So what are we doing today? We're wrapping up with radiation, right? What we discussed today goes in the final. And so what I want to do is introduce a few things to you. We'll do a problem, and then we have a big group hug, and we leave. So if you remember when we talked about radiation, one of the things we discussed is things like this, how different wavelengths and different orientations actually affect radiation. And I wanted to discuss this because there is many things that can be mysterious when you talk about greenhouse effect. How can it be, right? Light comes in, right? For example, greenhouse effect, you know how it works? In an actual greenhouse. So glass, is glass transparent to visible light? Yes, of course. Those of you with glasses know it for a fact, right? So, and the energy of the sun comes with its peak at this wavelength that is visible and brings all the heat into the greenhouse. Now the plants get hot and they want to lose heat, but they lose heat at something that is a lot lower than 7,000 Kelvin, right? So they want to lose heat at, 30, 40 degrees C. And that's into the deep infrared. Now, glass is opaque for those wavelengths, right? And that's a story. Like the same glass that let the radiation energy from the sun come in, now doesn't let the radiation energy of what is inside come out, right? That's one of the reasons, the main reason the greenhouse gets hot. CO2 has the same role. CO2 is transparent to visible light, but CO2 is opaque to thermal radiation, to infrared. So the energy of the sun comes in, hits the earth, wants to go out, but it can't because it cannot radiate to 0 Kelvin in the outer space. Instead, it radiates to the temperature of the CO2 layer, right? So right there, you understand global warming now, which is a pretty good thing for Canada, but you're not supposed to say it, right? Okay, so we discussed those things, but what I want to discuss, that is the last part, is let's now talk about the integral over all the wavelengths, and let's assume that the bodies are diffuse. That means they emit energy, regardless the angle, they emit the same, right? And when we make those two hypotheses that relate to black bodies, right, we can start doing calculations that you couldn't do before. So far, as of today, when you were calculating radiation, you were doing epsilon sigma T to the 4 minus T surroundings to the 4, right? That's what you were doing, and that's true. But it's true when you're surrounding all by the same temperature. Now, sometimes you're not surrounded by all the same temperature. Sometimes you're surrounded by a chunk at one temperature, a chunk at another temperature, a chunk at another temperature. And you want to calculate the heat exchange. Right this second, you don't know how to do it. In 10 minutes, you'll be awesome at that. So to do that, and that is not related to wavelength, it's not related to change of emissivity with orientation, we introduce this concept of view factor, right? And essentially, what we have there is how one element of surface sees another element of surface. Then, as we discussed, between two surfaces, we need to do a quadruple integral. An integral 2D of one surface multiplied by the 2D of the other one. 4D problem, right? And we're lucky because it could be 5D or could be 6D. So I'll take 4D anytime. And when you do this quadruple integral, you end up with this concept of view factor, right? Now, this view factor, which is still is a concept that is quite intuitive when you do a couple problems, and we're going to do one together, right? When you do this quadruple integral, you're going to see that it has some properties, and I'm going to write them down. So you write them down, and based on this, it's just like a brain puzzle solving radiation problems. So this in the book is 13.1.2. view factor relations. Right, and one was additive property. And what it says, if I have this surface AI that is emitting and then is surrounded by a surface here, surface AJ, surface AK, right, and whatever would be, right? Going to surface AN, what we have, the view factor F of I to the to the total, right, to the surroundings is Fij plus Fik, sorry, Fik plus Fin. Right? What this says is the view factor of these to the whole surrounding is the same as the sum of each other view factor. Right? And you start developing this intuitive concept how what this guy sees, because view factor, you can imagine you're standing here looking out. And if you say, what do you see? You see this and this and this and this and this. Right? It kind of makes some intuitive sense. You can start forgetting about the quadruple integral, which we will not do, and understand these properties. Then there's another rule. It's called the enclosure rule. And so if AI is completely surrounded, by AJ, so for example, this is AI, and this is AJ. Is AI completely area I, right? AI. Is it completely surrounded by AJ in this case, or is only half surrounded? What is it? Say? Okay, let's see. If I were to stand here, right? I would see all this, right? Would I see, and I should be even smaller, right? Do I see what is on the other side? No, right? Because if I'm tinier and tinier and tinier, that's my horizon, right? It's like a flat Earth, right? So this surface, and that's why I make the arrow pointing this side. I'm talking about this side and not that side, huh? So this side here is completely surrounded, right? And in this case, we have Fij equals 1. Isn't that awesome? You do the quadruple integral. 1. I love those. 3. Virtual surface. So imagine now I have my surface AI, and this is AJ. Now, that quadruple integral, let me tell you, it's tricky, right? Yet, the awesomeness of heat transfer and the great minds that preceded us figure out that if I replace AJ with this virtual surface, let's call it AV, I have that Fij, which is very difficult, is the same as Fiv, which is trivial. This is awesome. So, because you start to see how many problems that could be very difficult with some of these relations that are mathematical identities, they are true, become quite simpler. Another one that is called self-view. So, for example, if I have, this is AI. And I ask, I'm going to make this other one, and this is AI here. And I'm going to do the view factor, FII. So, in this case, or either of these cases, what can we say? For example, if I were to stand here, do I see surface AI? Well, maybe like this, right? But if I'm smaller and smaller and smaller, actually I don't, right? Because if I'm smaller and smaller, I would be seeing things, always seeing like Earth, right? If I go down to the ground, I'm going to see very little of the ground, right? So in this case, the view factor of the image with the surface with itself, 0. This is not the case here, because it doesn't matter how small I make myself, I can always see this other part, right? So this is different than 0, whatever it is. Some poor grad student probably had to do the quadruple integral. And I'm going to give you the last rule that is one of the most important. And it's called the reciprocity rule. And says, if I have Fij, so AI times Fij, right? This area times the view factor of this area is the same so it's not true that Fij is the same as Fji. Not true, but almost true, because it's just a ratio of areas, which is very easy to do. And very often, it's very difficult to calculate one view factor, but very easy to calculate the backwards view factor. And I'm going to show you an example on that. So, why I'm picking on black body radiation exchange. And the reason is because if I talk a bit about radiation exchange between two black bodies, whatever energy comes out of this black body goes to the other one, and nothing gets bounced back. Then the problem is just like a one-way ticket. I calculate things one way and happy. If I do a gray body analysis, emissivity is not 1, and if you remember, this Kirchhoff relation says that absorptivity is the same as emissivity. So if I were to have epsilon of 0.9, almost a black body, there is still 10% that is not absorbed. That means it's reflected. And whatever is reflected comes back, right? And then I need to analyze, okay, this guy gave me this radiation plus bounced back so much of my radiation. Right? So you have one of these infinite problems that go back and forth, back and forth, back and forth. There is a solution for that problem, and there is an awesome methodology of analysis that involves thermal resistance. We will not do that. We will finish our semester happily, assuming that everything is a black hole. And if you guys like gray holes, come to black holes. Black bodies. And if you like gray bodies, there's no gray holes. The black holes are not gray. If you like gray bodies, you just come and we discuss it. It's quite awesome. And the math is not much more different than what we are doing here. So if our exchange, black body radiation exchange, what we have, and we have all the steps of a derivation in the notes. But what you're going to have is that Q radiation, right, from a surface I is right, this means per unit area, right? And this means average. Look at that. This looks quite mathematical, but it's almost the same what you have been doing so far. There is a small difference, but it's a difference that matters very much. So look at this formula here. We have sigma. So we're talking about the radiation that comes in or out of surface I. Okay, so let's say that surface I, just for the sake of this example, is hotter than the surroundings. But it can be hotter than some and colder than some. But let's not worry about that. This formula is still the same and would not change. So how much energy is surface I emitting, right? What is the net thermal, the radiation power? And what it says is the sum of all the radiations from 1 to 2, I to j, I to k, I to whatever, right? So much like what we said when we talked about the additive rule. So we are going to add if the radiation out of the surface of this table to that wall, plus the radiation out of the surface of this table to the ceiling, radiation of the surface of this table to that wall, and like that, right? And we do this one to the fourth minus the other one to the fourth, just like you had been doing, right? Just the same thing. So Ti to the 4 minus Tj to the 4, I add them up. You have the sigma, the Stefan Boltzmann constant, right? 5.67 times to the 10 to the minus 8, right? Now, here's the difference that looks small, but actually is a big deal. In the formulas you had so far, you had epsilon sigma something, right? And now we have something that looks as if this was kind of some kind of a fake epsilon, has nothing to do with epsilon, right? Epsilon is 1. Epsilon is 1 because we are talking about black bodies. And if we wanted to be smart and put an epsilon here, we ruin everything. Because now means the thermal energy starts to bounce between the two surfaces. And this is not true anymore. So you're not going to see an epsilon in this formula. If you like your epsilon, I'll tell you how to do it. But we don't need to worry about that for the final. But what we have is Fij. And Fij has nothing to do with epsilon. Epsilon is 1, but Fij says how much of this space, when this table is radiating, right? That wall on my left is only part of all the space, right? So how much of this radiation goes there? That's a view factor. How much of this radiation goes to the ceiling? That's a view factor to the ceiling. How much of this radiation goes to the board? This is a view factor to the board. All right? So this is how much of its surrounding is seeing. It's always the same story. Quadruple integral, lots of complexity. Some professor got the grad student, tortured them for 3 or 4 years. They get a PhD. And you guys get these integrals. And these integrals doesn't look like an integral anymore. Plug and chug. Plug and chug. For example, Fij, right? So we have surface I here, surface j here, or I here and j here, or these two ones, right? I and j. And you say, okay, I want to know what the Fij is for these two configurations. This is 2D geometries, right? So that means they are very long into the screen, right? It's like two plates, very long plates next to each other, right? This is like, you know what? When you're waiting for the LRT in winter and you have this radiating thing there on top, this is your radiating thing. This is the bottom of the shelter, and this is you freezing there, like, right? Okay, so, and you say, what the hell is this Fij? Okay, I look at the formula. Fij is Wi minus Wj. This is the small w over L, right? And L is the separation. So that's the big W here. And you put it there. Plug and chug. Plug and chug. And you got the Fij. You like this other one. Fij is given by this sine of alpha. Straight. Now, look. Do you like your plane rows, a row of cylinders? Doesn't that look like a heat exchanger? We didn't mention this when we did heat exchangers, but you want to do a heat exchanger with flames and radiation? You got it. You got everything. And more. If you want to do 3D geometries now, like not just things that are very long and out of the plane, but actual 2 rectangular plates, right? You can calculate it. Now it gets a lot more like involved, right? Just plug and chug. You would do it in Excel. You'd be a happy person. 2 squares, 2 circles, right? what you're going to see in your formula sheet is the embodiment of these formulas in the form of graphs. These graphs are somewhat similar to those graphs of heat exchanger efficiency, right? You have X, Y, and L for the case of the two rectangles, X over L and Y over L, and there you get your view factor. Same if you have two circles, same if you have like an open laptop here, right? So the biggest difficulty here was to get these curves. Somebody did it for you, just take the money and run, right? This will be in your formula sheet. Okay, that's the derivation about blackbody radiation exchange that is in your notes, but this formula here is the bottom of this. Just the last day of class, let's spare the derivations, but it's a very easy one.